Recall the equation of motion for an undamped multi-degree of freedom system. mx double dot plus kx equals f of t. We'll now apply the properties of eigenvalues and eigenvectors to develop efficient methods of solving for the natural frequencies and mode shapes of the system and the response in both free and forced vibration. In prior work, we showed that the solution for a multi-degree of freedom undamped system was equivalent to solving the matrix problem k minus omega squared mu equals 0. Expanding out the determinant of this matrix yields a characteristic polynomial whose roots were shown to be the undamped natural frequencies of the system. Once the natural frequencies were obtained, the mode shapes were obtained by solving this expression for the vectors u sub I for each natural frequency omega sub I. In this lecture, we will demonstrate how the solution of the undamped multi-degree of freedom vibration problem can be related directly to the solution of an eigenvalue problem for a real symmetric matrix. Once we have cast the problem in this form, we will immediately apply the properties of eigenvalues and eigenvectors to transform the problem into the solution of a set of single degree of freedom oscillators. Each single degree of freedom oscillator can then be solved independently, and the solution in modal coordinates is then transformed back to physical coordinates to obtain the solution of the original matrix differential equation. This process is called modal analysis. To begin, let's recall that under certain circumstances we can find a matrix called the square root matrix that when multiplied by itself yields the original matrix. For general matrix A, this concept is shown in the top expression on the chart. The square root matrix of A is denoted a to the 1/2. It is an n by n matrix that satisfies the expression a to the 1/2, a to the 1/2 equals a. If the square root matrix of A exists, then we can also find the inverse of the square root matrix, a to the minus 1/2, that when multiplied by a to the 1/2 yields the identity matrix. Reducing the general expression for multi-degree of freedom systems to that of a free vibration problem results in the matrix expression mx double dot plus kx equals 0. If this matrix expression represents the vibration of a mechanical system, under almost all circumstances we can find the square root of the mass matrix, denoted m to the 1/2. Rewriting the mass matrix as the product of m to the 1/2 and m to the 1/2 yields the expression at the bottom of the chart. The two expressions on this chart are equivalent. We have simply rewritten the mass matrix in terms of its matrix square root. At the outset of this analysis, we said that applying the concepts of the eigenvalue problem will yield a simpler set of equations to solve. This is achieved by applying a coordinate transformation in which the variables that represent the physical degrees of freedom x of t are transformed into another set of variables we call q of t through the transformation x of t equals m to the minus 1/2 q of t. Since we assume that the inverse square root of the mass matrix is independent of time, the second derivative of x of t is simply equal to the inverse square root of m times q double dot. Substituting this coordinate transformation into the equations of motion yields the expression shown at the top of the chart. Pre-multiplying this expression by the inverse of the square root matrix simplifies the expression considerably. The four matrices that pre-multiply q double dot are shown to be equivalent to the multiplication of the identity matrix times itself, which of course is simply equal to the identity matrix. The matrix product m to the minus 1/2 k m to the minus 1/2 is simply denoted k tilde. The application of this coordinate transformation yields a matrix expression in which an identity matrix pre-multiplies the second derivative term and a transformed stiffness matrix multiplies the term q of t. One way to envision this transformation is that we have mass normalized this system of equations by transforming to a coordinate system in which the mass matrix is the identity matrix. Likewise, the stiffness matrix has been mass normalized since it is pre and post multiplied by the inverse square root of m. The transformation to a mass normalized system will allow us to understand how we can apply the properties of the eigenvalues and eigenvectors to the solution to the multi-degree of freedom vibration problem. The mass normalized stiffness matrix is itself a real symmetric matrix. For this reason, we know that there are a set of eigenvectors u that will diagonalize the matrix into a matrix of eigenvalues. Call the matrix of eigenvectors of k tilde P. P is an n by n matrix of eigenvectors of k tilde that will diagonalize the matrix into a matrix of eigenvalues. Now imagine applying a second coordinate transformation from the mass normalized coordinates q of t to a set of modal coordinates r of t through the transformation q of t equals p r of t. Substituting this expression into the equations of motion in terms of q of t yields the bottom expression on this chart. At this point in the analysis, we've not gained much since we now have a system that is once again a coupled set of ordinary differential equations in r of t. The real value to this coordinate transformation becomes apparent when we pre-multiply the equations by the transpose of the eigenvector matrix P. We know from the solution of the symmetric eigenvalue problem that P transpose P is equal to the identity matrix, and the matrix product P transpose K tilde P is the diagonal matrix of eigenvalues of K tilde. Rewriting the expression in modal coordinates yields the equation IR double dot plus lambda R equals 0, where lambda is a diagonal matrix of eigenvalues of K tilde. These are, by definition, the square of the natural frequencies of the undamped system. What is more important, though, is that the matrix expression on the bottom of this chart represents a set of n uncoupled differential equations. We can see this more clearly by expanding out the matrix expression in modal coordinates. Once again, because of the properties of the eigenvectors and eigenvalues of a real symmetric matrix, we know that transforming the system to modal coordinates yields a set of n uncoupled differential equations. Each equation can be envisioned as an independent, single degree of freedom oscillator in the modal coordinate r sub I. This can be seen more clearly by writing out each equation in the matrix expression. Once the system has been transformed into modal coordinates, the equations represent a set of n uncoupled equations of the form r sub I double dot plus omega sub I squared r sub I equals 0. From our analysis of single degree freedom systems, we know that we can solve each equation independent of one another if we have the set of initial conditions for each modal coordinate. The initial conditions are obtained by applying the coordinate transformation from the physical coordinates x of t to the modal coordinates r of t. We made this transformation in two steps. First from x of t to q of t, the mass normalized equations, and then from q of t to r of t, the modal coordinates. These two steps can be combined through excessive application of the coordinate transformations as shown in the top expression. The result is a coordinate transformation that takes us directly from x of t to r of t. It is x of t equals the inverse square root of m times the eigenvector matrix P. Inverting this transformation as shown in the bottom expression yields the coordinate transformation from modal coordinates to physical coordinates. Now the transformation to modal coordinates has been attained, we can readily see that the initial conditions in modal coordinates are obtained by transforming the initial conditions in physical coordinates to modal coordinates through the expression obtained on the previous chart. Both the initial conditions for displacement and the initial conditions for velocity can be obtained in this manner as shown in the top two expressions. From the analysis of single degree freedom systems, we know that the free vibration of a single degree freedom oscillator is given by the expression on the bottom of this chart. This expression is applied to each of the n modal coordinates independently. For each modal coordinate, we use the corresponding natural frequency, initial modal displacement, and initial modal velocity to obtain the values of the amplitude and phase of the free vibration response. It's important to note that in many cases the initial condition in physical coordinates may be a sparse vector. In other words, the initial condition x of 0 and x dot of 0 may only contain a few non-zero elements. In general, though, the transformation from physical to modal coordinates will yield a fully populated vector of initial conditions. Thus, while only a small subset of physical coordinates may be displaced at time 0, in general the initial conditions in modal coordinates will be mostly non-zero. The final step in the analysis is to transform the modal solutions back into physical coordinates. This is achieved by constructing a vector of time-dependent solutions for the modal coordinates and then applying the coordinate transformation as shown in the expression on this chart. As we discussed previously, this expression reinforces the idea that the solution of an undamped multi-degree freedom oscillator is a linear superposition of modal coordinates. Now, in the previous analysis, we performed two coordinate transformations to obtain a set of decoupled ordinary differential equations that could be solved independently for each modal coordinate. First, we normalized the mass matrix to be equal to the identity matrix by transforming the equations into a coordinate space defined by Q of t. And then we diagonalized the system by using the eigenvector matrix of the mass normalized stiffness matrix to transform the system into modal coordinates r of t. The coordinate transformation can be performed in one step by defining a matrix S that is equal to the coordinate transformation from x of t directly to r of t. The matrix S is simply the product of the inverse square root matrix of M and the eigenvectors of the mass normalized stiffness matrix P. Combining these transformations results in a direct relationship between x of t and r of t, as shown in the expression on this chart. Now we can see from this relationship that the matrix S is simply equal to the mass normalized mode shape matrix. Each column of S is a mode shape that has been normalized with respect to the mass matrix. The normalization of the mode shape matrix S can be seen by substituting the coordinate transformation into the equations of motion and pre-multiplying by S transpose. The definition of the matrix S results in a one-step diagonalization of the equations of motion. The equations of motion in modal coordinates are once again a decoupled set of differential equations that can be solved independently using the methods for single degree of freedom systems. The relationship between the initial conditions in x of t and r of t are defined in terms of the inverse of the mass normalized mode shape matrix S. Once the initial conditions in modal coordinates have been obtained, they can be applied to each of the modal solutions to obtain the amplitude and phase of each modal coordinate. So in summary, we have shown that the solution to the free vibration problem for multi-degree of freedom systems can be related directly to the solution of an eigenvalue problem of a real symmetric matrix. The orthogonality of the eigenvectors and their ability to diagonalize the equations of motion result in an efficient method of solving the coupled ordinary differential equations that represent multi-degree of freedom vibrating systems. In this chart, we describe this approach. Given the set of n coupled ordinary differential equations that represent the multi-degree of freedom vibrating system, we first transform the equations of motion to a set of modal coordinates through the use of the mass normalized mode shape matrix S. The result is a set of n ordinary differential equations in modal space that are decoupled, allowing them to be solved independently by applying the initial conditions for each of the modal coordinates. Once a solution for each modal coordinate has been obtained, the set of modal responses are transformed back to physical coordinates using the mass normalized mode shape matrix S. The result is a set of n responses x of t, which represent the solution of the original set of ordinary differential equations. This diagram reinforces the fact that the solution x of t is a linear superposition of the response of the n modes of the system. Each mode is characterized by an undamped natural frequency and a mass normalized mode shape. The solution x of t is a linear superposition of the response of each modal coordinate.